Welcome back to the Basic Electronics series, and today we will learning about AC circuits and sinusoidal analysis. Here is the agenda: AC circuits, terms related to AC circuits, peak RMS values and effective or RMS value, form factor and peak factor, analysis of single phase AC circuits consisting of RLC, then concept of reactance, impedance, susceptance and admittance. Then AC circuits. The flow of electricity can be done in two ways, like AC and DC. So this is the AC. Here flow of electrons will change their directions, like going forward and then going backward. So this is continuous with respect to time. But in DC, the flow of electrons will be in single direction, or it is in discrete with respect to time. Then terms related to AC circuit. So when an alternating quantity goes through complete set of positive and negative values, so this is positive and this is negative, or goes through 360 electrical degrees. So alternation is nothing but one half cycle. So the time taken to complete one cycle is nothing but time period. Frequency is inverse to the time period. So frequency is nothing but number of cycle made per second. Amplitude, so this is the amplitude. You can also call it as peak or maximum value. So it is nothing but maximum value attained by an alternating quantity in one cycle. So here is also their amplitude. So next is the peak RMS values and effective or RMS value. So peak value we already seen in the previous explanation. Next is the average value. So average value of a periodic waveform. So you can consider any waveform, sine wave, square wave or triangular wave. So average value is defined as the quotient of the area under the waveform with respect to time. So in other words, the averaging of all the instantaneous value along the time axis with the time being one period. So it is like same. How you find average? Sum of all the values divided by number of values. Like that here, averaging of all the instantaneous values along time axis with the time being one full period. You can see average value in this example, in this second diagram. It represents the average value. Next is the effective or RMS value. So RMS is nothing but root mean squared. So it can also call it as effective or heating value of alternating current. So what it will do means it would provide the same amount of heat generation in a resistor as the AC voltage would if applied to that same resistance. So here you can see the RMS or effective or RMS value. So in practical, assume you are at a party with music playing. So the peak is like the loudest beat. It is the maximum energy moment. So but what is the overall loudness? That's like the RMS value. It gives you the average energy or how loud the music feels overall. So now you got idea what is peak value. It is nothing but the loudest point, like the loudest beat. But RMS value is nothing but the effective heating value, like the continuous energy. This tells how much work it does. right? For a sine wave, RMS value is 0.707 into peak value. And next is the form factor and peak factor. So form factor is defined as the ratio of RMS value to the average value. So for sinusoidal alternating voltage, form factor is 0.707 em divided by 0.637 em. For current, 0.707 em divided by 0.637 im. So this im will cancel with each other, here em also. Then 0.707 divided by 0.637 is nothing but 1.11. And peak factor is nothing but the ratio of maximum value to the RMS value. For sinusoidal alternating voltage, so maximum value is em, RMS value is 0.707 em. So em will cancel with each other. 1 by 0.707 is nothing but 1.414. Similarly, find im for alternating current. Next is the analysis of single phase AC circuits consisting of RLC. So it is purely resistive or non-inductive circuit. So here purely resistive means there is only R will be there, R circuit. So in this circuit which has inductance so small that at normal frequency its reactance is negligible as compared to its resistance. So here we will have only the resistance, that is R ohms, that is connected across the sinusoidal voltage, this one. So that is V equals to V max sin omega t, and here current is flowing. As already said, the current flowing through pure resistor changes. So there is no back EMF is set up. So applied voltage has to overcome the ohmic drop of IR only. So from the Ohm's law we know V equals to IR. But to get the value of I, we should rearrange this equation. Then I equals to V by R. But from the circuit we have V equals to V max sin omega t. So substitute here. When current is maximum means when omega t is equals to pi by 2. But we already know sin pi by 2 is nothing but 1, right? So I max becomes V max by R. So this term will become 1. Sin pi by 2 means 1. And instantaneous current may be expressed as I equals to I max sin omega t. So now you having applied voltage and instantaneous current formula. From these two, by considering these two, you can tell it as in pure resistive circuit, the applied voltage and current are in phase with each other, right? So I max is V max by R. So these are in phase with each other. So see in this diagram, so current is flowing where V is there, that phase only. So these are in same phase or in phase. So in the circuit diagram you can see V and I both are in same phase. But power is in different phase, right? So here power is in positive, but I and V both are negative. Why? Because power means V into I. Here V and I both are negative means power should be positive. So minus into minus will be plus. So next is the purely inductive circuit. So an inductive circuit is a coil. Coil means this is inductance. So with or without an iron core having negligible resistance. Here we considering only the inductance. So practically pure inductance can never be had as the inductive coil has always small resistance. So however, a coil of thick copper wire wound on a laminated iron core has negligible resistant area, that is known as the choke coil. So see, in this diagram we having reactance and current is flowing and applied voltage V is nothing but V max sin omega t. So when an alternating voltage is applied to a purely inductive coil, means when you apply this voltage to this purely inductive coil, so an EMF known as self-induced EMF is induced in the coil. So that is nothing but EL, that opposes the applied voltage. So since coil has no resistance, at every instant applied voltage has to overcome this self-induced EMF only. So we know V equals to V max sin omega t. Already you can see here V equals to V max sin omega t. And self-inductance of coil is nothing but L Henry. Self-induced EMF in the coil is EL. So that is equals to minus L di by dt. So since applied voltage, here we said, right, applied voltage at every instant is equals to or opposite to the self-induced EMF. That means V equals to minus EL. Now substitute the values. V means V max sin omega t, EL means minus L di by dt. So this minus and this minus becomes positive. So then this move L to left side and dt to left side. That time L is becomes V max sin omega t divided by L. Dt is multiplying. So di equals to V max divided by L sin omega t dt. So here we got di value, but what we want? Current value, right? So I value we need. So take integration on both sides. Integration of di is nothing but I. So this is the constant term, write as it is, then apply integration. So integration of sin omega t is nothing but minus cos omega t divided by omega plus integration constant, that is nothing but A. So it is 0 from initial conditions. So write rest right as it is. So I equals to minus V max omega L cos omega t. But minus cos omega t, you can write it like this, sin omega t minus pi by 2. So here you can observe that I means current lags B. So here current is lags voltage by pi by 2, means 90 degree, right? So from the expression of instantaneous applied voltage and instantaneous current flowing through this purely inductive circuit, so you can observe that current lags behind the applied voltage by pi by 2, means 90 degree. So here current is lagging. So let's draw the same thing in phase diagram. Okay. So here current is lagging. Current lags behind the applied voltage by pi by 2, means 90 degree. And draw the wave diagram. So we draw as it is, but current lags pi by 2. Here current is lagging. You can observe in the dotted wave current is lagging, and power P equals to V into I is nothing but power. So inductive reactance is nothing but XL. So omega L in the expression I max equals to V max by omega L is known as inductive reactance, and that is denoted by XL. So XL is nothing but omega L. L is in Henry and XL is in ohms. Next is the purely capacitive circuit. So this is. So it is nothing but when the DC voltage is impressed across the perfect condenser, so it will charge it to full voltage almost instantaneously. So the charging current will flow only during the period of build-up, and it will cease to flow as soon as the capacitor has attained the steady voltage of the source. So this implies a capacitor is a break in the circuit or infinitely high resistance. So that is nothing but purely capacitive circuit. So here we having capacitor and current is flowing, and we having voltage V equals to V max sin omega t. So the expression for instantaneous charge is given as Q equals to C max C V max sin omega t. So here capacitor current means I is equals to rate of change of charge. So the capacitor current may be obtained by differentiating this Q equation. So rate of change of means derivative of Q with respect to time. Now substitute the Q value here. So the differentiation, right? So take the constant term. So write it first, C V max, then sin omega t. So apply the derivation with respect to time. So derivation of sin omega t is nothing but cos omega t into omega. So therefore V max, then you can write it omega c as 1 by omega c. So that is both are same. If you write like this also same, if you write like this also same. Then cos omega t, you can write it as sin of omega t plus pi by 2. When current is maximum, that time t is equals to 0. So when t is equals to 0, omega also 0. So V max equals to, I max equals to V max divided by 1 by omega c. So sin pi by 2 we get, right? So sin pi by 2 is nothing but 1. So we will get only this term here. So I max equals to V max divided by 1 by omega c. So now you need to substitute this I max value in here. I equals to I max sin of omega t plus pi by 2. So here what you can observe, so current leads being the applied voltage by 90 degree, right? In the previous purely inductive circuit, current is lagging, but here current leads the applied voltage by pi by 2. And here we having 1 by omega c. So I max equals to V max by 1 by omega c. This 1 by omega c is nothing but capacitive reactance. It can be denoted as XC. So XC is nothing but 1 by omega c. C is in farad, so omega is in radians and XC is in ohms. So next is the resistance capacitance series circuit. So in this circuit, so R and C, R is in ohm and C is in farad, means these are the units. These both are connected in series. So supply frequency is F hertz and current is flowing right through the circuit. The unit of current is amps. The voltage across this R resistance is nothing but VR, and voltage across the capacitor is nothing but VC. So VR, from the Ohm's law we know V equals to IR. VC is nothing but IXC, lagging behind I by pi by 2 radians or 90 degree. So the applied voltage, so V means magnitude of VR and VC. So we can write it like this: V equals to square root of VR square plus VC square. But we know that VR is nothing but IR and VC is nothing but IXC. Substitute. So I is common, so take outside, then write as it is. So R square plus XC square is nothing but Z. Square root of R square plus XC square is nothing but Z. So that is nothing but impedance. So you will get the final answer is IZ. So total voltage is nothing but IZ. So that you can see here. So here we need to take current as a reference vector. So VR is nothing but IR. So this is the taken in phase with the current vector. So we know, right, resistance is in phase. Pure resistive circuit, we know, right, resistance is in phase with the, current is in phase with the voltage. So these VR and I is in phase, same phase. We should draw VR in same phase. Next VC. So VC is, we got to know from the pure capacitive circuit. So here current leads voltage by 90 degrees, right? So you need to write VC like this. So the total voltage is nothing but V equals to IZ. So the magnitude of VR and VC is nothing but I. So you need to write here. So this is the phasor diagram. Now you need to find tan F and cos F. So tan F equals to VC divided by VR. Right, VC divided by VR. Substitute IXC divided by IR. I will get cancelled with each other. XC by R. But XC is nothing but 1 by omega C. Substitute, then you will get like this. So phi equals to tan inverse of 1 by omega RC. This is the phi value. Now you need to find the power factor. That is nothing but cos phi. So cos phi is nothing but VR divided by V, total V. So VR is nothing but IR divided by IZ. I will cancel with each other, then you will get this value, R by Z. So V is nothing but V max sin omega t. I is nothing but I max sin of omega t plus phi. So power means V into I, that is power. Next is the RL series circuit. So here we need to connect R and L in series. R means resistance, L means inductance. This is in ohms and this is in Henry. So when AC supply voltage V is applied, the current I flows in the circuit. So V means V m sin omega t. So IR and IL will be the current flowing through the resistor and inductor respectively, and VR and VL means voltage. So VR is the voltage across the resistance and VL is the voltage across the inductance. So this is the phasor diagram. So here also we need to take current as a reference. The voltage drop across the resistance VR drawn in phase with the current. So VR is in phase with the current. Next is the voltage drop across the inductive reactance. So we already know, so in the pure inductive circuit, from the pure inductive circuit, their current lags being applied voltage by pi by 2. So we need to draw VL like this, and V is nothing but the magnitude of VL and VR, vector sum of two voltages, that is VL and VR. So you need to write V here. So this is the phasor diagram. So in the right angle triangle, means OAB, this one, VR equals to IR and VL equals to IXL. So see here, we already know VR equals to IR. So VR equals to IR and VL means IXL. So V means VR square divided by VL square. Then substitute, then you will get, so I is common, so take outside, then R square plus XL square. So this is nothing but Z, substitute, then V equals to IZ. So I means V by Z. So Z means this is the impedance. So total opposition offered to the flow of AC by an RL series circuit. So this is called the impedance, and we can measure it using the ohms. So we find, now you need to find the tan phi. So phi is here. Now apply tan. So tan phi equals to VL divided by VR, right? VL divided by VR. Substitute the values. I will cancel with each other, XL by R. So phi means tan inverse of XL by R. So power means P equals to V into I. Substitute. Next is the RLC series circuit. So here RLC means pure resistance, pure inductance, pure capacitance. All are connected together in series combination with each other. So all three are connected in series. So current flowing in each element of the circuit will be same as the total current I flowing in the circuit. Here we applied V. V means Vm sin omega t. The voltage across R is VR, voltage across L is VL, and voltage across C is VC. Total voltage is V. So in RLC circuit, we having XL is here nothing but 2 pi FL. Means XL is nothing but omega L. So omega is nothing but 2 pi F. Similarly, XC is nothing but 1 by omega C. Omega is nothing but 2 pi F. So when the AC voltage is applied through RLC circuit, the resulting current flows through the circuit, and thus voltage across each element. VR is nothing but IR, VL is nothing but IXL, and VC is nothing but IXC. So this is the phasor diagram. So this is the steps. So the voltage across the inductor L, that is leads the current I by 90 degree angle. So L is here, L is leading the current by 90 degree, and C is lagging the current by 90 degree, and R is in phase. So this is the total voltage V. So VL and VC are opposite to each other. So in RLC circuit, okay, VL and VC are opposite to each other, and VC is lagging the current I by 90 degree, and because in capacitive load and current leads the voltage by an angle 90 degree, and here this voltage across inductor L. So here VL leads the current by 90 degree. So see here, VL and VC are opposite to each other, right? So V equals to VR square plus VL minus VC square. We know the value. VR means IR, VL means IXL, VC means IXC. Substitute here. I is common, so take common. Next, remaining write as it is. So this is nothing but Z. So V by Z. I equals to V by Z. So Z is nothing but R square plus XL minus XC square. So here also R is nothing but impedance. Means it is the total opposition offered to the flow of current by an RLC circuit. To find the phase angle, we know tan phi, right? Apply here. So tan phi equals to this one, VL minus VC divided by VR. So substitute the values. VL means IXL, VC means IXC, VR means IR. So I is cancelled with each other. So this is I is a common term, so cancelled. Now phi means tan inverse of XL minus XC divided by R. Power means VI cos phi. So substitute V and I values, then you will get the value of power. Power factor means cos phi. So in this, so cos phi is nothing but VR divided by V. That is nothing but IR divided by IZ. I cancel with each other, then you will get R by Z. So when XL is greater than XC, the phase angle phi is there, right? That is positive. So then it will behave as RL series circuit. So in which current lags behind the apply voltage. Then power factor is lagging. But when XL is less than XC or XC is greater than XL, the phase angle phi is negative. Then the circuit is acts as a RC circuit. So here current leads the voltage by 90 degree. But when both are equal, the phase angle is 0. That time circuit behaves like a purely resistive circuit. So that time current and voltage are in phase with each other. Then power factor is unity. Next is concept of reactance, impedance, susceptance and admittance. So reactance is nothing but we already seen in the previous circuits. Inductive reactance, capacitive reactance, that is nothing but XC, XL. So reactance is nothing but X. So it is nothing but opposition to AC current due to energy storage in electric or magnetic fields. It is like resistance. So it is found in capacitors and inductors. So it causes voltage and current to be 90 degree out of phase. Either it is lags 90 degree or lead by 90 degree. It is measured using ohms and represented using the symbol X. Next is the impedance. This is also opposition but total opposition to AC current in a circuit. This is not total opposition but this is total opposition. So it combines both the resistance and reactance. We have seen Z equals to square root of R square plus X square like that. So it combines both. So present in all AC circuits and components. It causes voltage and current to be 0 degree to 90 degree out of phase. So it is also measured in ohms. It can be expressed as Z equals to R plus JX. Symbol is Z. Next is the susceptance. It can be represented using the symbol B and unit is Siemens. So susceptance means it is a imaginary part of the admittance. So it is represented ease of current flow due to capacitance or inductance. It is opposite concept of reactance. And admittance we can represent using the symbol Y, and it is also measured using Siemens. So Y equals to G plus JB. So this is the imaginary part. B is susceptance. G means conductance. So admittance is nothing but the reciprocal of impedance or total ease of current flow. So Y equals to 1 by Z. So Z means impedance. That's all about the AC circuits and sinusoidal analysis. For more videos, watch the upcoming classes. Thank you all.